I am very happy to introduce our speaker, Jiajun today. Jiajun is an assistant professor of computer science at Stanford University. As most of us know, we've been following your work for some time. He works in computer vision, machine learning, and computational cognitive science. Before joining Stanford, he was a visiting faculty researcher at Google Research, and he received his PhD in the EECS department at MIT. His research has been recognized through the ACM Doctoral Dissertation Award, honorable mention, the AAAI ACM SIGAI Doctoral Dissertation Award, the MIT George M. Sproul's PhD Thesis Award, and so many more. So we are extremely fortunate to have Jiajun speak with us today, and we're very excited to see what you're going to be talking to us today about. So over to you.
Okay, thanks for having me, and thanks for the nice introduction, Prabha. Now I sort of regret, because now I realize this is actually more vision than robotics. Because last week at New York City for RSS, I was asking Carl 2 weeks ago. I was like, maybe I should do this in person. But then Shuran told me that the robotics people are not going to be around. But if this is the vision seminar, it doesn't matter if the robotics people are around or not. So I should probably just do it last week in person. But anyway, it's okay. So I'm going to talk about the visual world, understanding visual world through code. Our world is beautiful and nice, and you can see all those, now you have all those nice models, generative models, especially for capturing the details and textures and stuff like that. And, especially those trained on very large, vision language models. But in addition to all those details, right, there's another aspects of the world which is also important, and I think in some sense kind of fundamental to human intelligence as well. That is the notion of the structure. So especially if you look at things that are man-made, human artifacts, then there are a lot of rich structures in the visual world, things that are totally like rectangular or circular, or things that are symmetric, right? There's the notion of planes and the notion of symmetry, which, perfect symmetry doesn't really exist in the natural world, but somehow human come up with that for a reason, maybe for aesthetic reasons, or also for practical reasons, right? So looking at the corridors, looking at the buildings, there are a lot of planes, and there are symmetries, reflectional symmetry, rotational symmetry, and there are repetitions, right? We want those kind of structures to be regular, stuff like that. So we perceive that, instantly without any efforts. So we wonder, how can we leverage such structural information for scene understanding and editing? So here is a demo of what we want to achieve. So we put our algorithm into this Adobe Photoshop GUI. So it is actually our algorithm that allows you, first there's interactive segmentation, which is provided by Adobe Photoshop. So you can do interactive segmentation. And then, you want to compute the vanishing point of the scene, of the objects, and then powered by our algorithm, you can, based on the vanishing point estimated, you can actually, for example, make the building taller. But here, you not only want it to be, of course, you want it to be physically realistic, and also respecting the 3D structure, right? There's perspective going on, so you want it to be, close things that are closer to appear to be larger, but also you want to respect the regularities, right? There are kind of a number of windows there, and they're like different stories, and you want them to repeat as what we would expect. So how can we do this? Originally, we were inspired by some kind of interesting work on using program synthesis for visual data. This is, joint work with, not my work, but the joint work with a number of people back then, all from MIT, and actually at Brown as well. Kevin Ellis, Daniel Ricci, Armando, and Josh Tenenbaum. What they did is they have like an observed image, like those kind of sketches. But these are human sketches, but clearly there's some structure going on. So they're like, is it possible for us to first infer some geometric primitives, right? In some sense, you can think about it as a vectorize this rasterized image. You have a rasterized image, you're going to vectorize it so that you have lines and rectangles. And then based on those kind of primitives, you're now working in kind of a much lower dimensional symbolic space, and you can have program synthesis to try to infer the structures of the program structure of the patterns in the image. And once you have the program, allows you to do some other things. I think eventually, if you want to communicate with humans, one way to communicate with humans is through language, and the other is through those kind of, or at least when we program, where we communicate with humans, with each other through these kind of high-level structures. So you can easily change the program, allows you to do things like extrapolation. So now you have a larger pattern. So we did some initial exploration that was back in 2019 to extend it to 3D, where you can, if you live in this kind of contrived world where things are just geometric primitives and 3D, in 3D, then you can also do similar program level synthesis. You can put them together, put this kind of high level program structure together with GANs or image generation networks, so that allows you to not only edit the scene, but also translate it back to real scenes, so that you can change the pattern. You can have an input image, you can infer such kind of program structure, allows you to add another column of the objects or stuff like that, right? But here, clearly the limitation of this and the line drawing work is you have to assume what the set of primitives are. Right, so in 2D, it's lines and rectangles. In 3D, it's spheres and cylinders and stuff like that. But we don't live in this kind of contrived world. So of course, in computer vision, we want to generalize that to natural images. And so then the question naturally becomes, what are the primitives in the natural world that if you want to describe scenes with this kind of program representation? So here's an image of American serials, and clearly there is some kind of structures with the serials, but what is the primitive here, right? Is that a cylinder? Is it a sphere? That's probably not. So we thought that's not going to generalize. If you wanted to generalize to the natural images, then you have to have something that is a bit principled. And we look into this idea. Mihail Irani from Israel has been working on this for like decades, right? Called internal learning or single image learning. Now it has become kind of even more popular for other reasons, like nerve and those kind of stuff. But even before those neural rendering stuff, I think some people have been looking into the idea of learning from a single image, because there are a lot of, it goes back to the early ideas about image statistics, right? What really makes an image? Because there are a lot of structures in image, a single image by itself. For example, if you look at the image at the bottom left, you can see that a lot of patches, they're really similar and they're repeating themselves. Such kind of repetition can happen at the same scale, or it can happen at different scales. And it happens at different scales because these are essentially the same objects, but because of perspective, right? Objects that are closer to you appear to be larger. So such kind of repetitions appear at different scales. So within the single image, even the patch statistics or image statistics, there's a lot of signals that tells you, okay, what are the things that really appear to be repeating themselves, or what are the things that really exist from that single image. So in 2017, they had this idea about integrating this idea of internal learning with deep learning. So what they did is they take an image and then you can send it to a pre-trained deep neural networks. Say this is like an AlexNet, pre-trained on ImageNet. And you can take the feature responses from AlexNet in like layer 2 or 3, and then you can try to translate the feature maps. And the goal is to find the displacement, which in X and Y, in horizontal and vertical axis, that maximizes the correlations between these feature maps, right? So by finding the displacement that maximize the correlations, that means, okay, these are most likely, such displacements are most likely to be the gap between two, repeating objects, right? So here, by using these methods, they're able to identify the centroids of these repeating objects. And the idea of, using this kind of feature maps instead of just raw pixels is hopefully, you become a bit more robust to changes like lightings and noises and occlusions and stuff like that, right? Because that's what these CNNs are supposed to be trained to recognize. Okay. Yeah, so we adopted this idea. Of course, we make some changes to it. So then we're able to identify without annotations the centroids of these repeating objects. And then now, in some sense, you can think about it as now we've also vectorized the image, right? So we don't, it's not like line drawings, but still you have a rasterized image. Now you have vectorized it. You have this centroids. You work in this kind of much lower dimensional space, and you will be able to synthesize a program just based on the positions of these centroids. And what is the low-level primitives that can be parameterized by, for example, a generative network. So if you adapt this idea to other images, like here is the image of number of crosses, and one cross is missing, so you want to solve the problem of inpainting. And the program can actually guide you and suggest to you, okay, what are the patches? What should really be there, right? No, of course, there's no ground truth. Anything can be there. But inpainting is to find something that's possible to humans, to us. Then we will feel like, oh yeah, there should be a cross there as well. So the program allows you to or suggest to you that, okay, then you should look at these other patches, which are the positions of these patches are suggested to you by the program. Then you can send them, to train additional generative network, conditional generative network, allows you to inpaint the missing region. So it will look, kind of plausible to me. And it's not like simply copying patches from elsewhere. If you look at this cross versus others, they're all kind of slightly different, right? So it's not like directly copying patches, which also works pretty well if you manage to make it work. But here, we want some slight variations, which is actually produced by this conditional generative network, but also looks, very natural, and allows you to other things like, what they can do with the line joins, including extrapolations. What if you want to add another row of the process, and deviation magnification, right? So sometimes there are things that are not perfectly aligned, and by having this program repetition, you actually have an idea about, okay, what that deviation is, right? How large it is. Then you can magnify it. You can further change, edit image to make it look more irregular or more regular. Going back to the serial image, you can do similar things, including inpainting, inpaint a missing serial, add another column of serials, and irregular or regularity editing on these images. Okay, so these are all from I would say everything is like you look at from a top-down view, right? So in practice, you often look at things from a perspective, right? So here you see an image from an angle, and then you're like, okay, yes, there are still some regularities there, but it is not like it's like you have to consider the role of perspectives. So we want to so in the follow-up work, we thought about, is that possible for us to incorporate camera poses? So then the question is, you want to first infer the camera poses, and then you want to use that to rectify the image. So once you rectify it, that gives you a signal of now you're seeing objects, from a top-down view, and they are now their positions are more on the regular grid. Then you sort of reduce the problem to the problem earlier that you can, what you can already solve, right? So now you want to do two things at the same time, including inference camera process as well as visual program synthesis. And the insight here is these problems, they should really help each other and should be solved jointly. So if you're only solving one of them without considering the other, it is very challenging. If you have an image and then you say, okay, I just want to directly estimate camera poses like planet, and then it just doesn't work that well. Or if you directly apply the method we had talked about before, of course it doesn't work, right? Because it doesn't really have this kind of regularity structure. So we try to have this idea of doing a kind of joint iterative inference. Intuition is very simple, right? Only if you can estimate the camera poses correctly, you will be able to rectify the image. Then your infer program repetition should be simple, right? So there's kind of this kind of simplicity prior here, and only if you estimate the program correctly, then if you can estimate the program correctly, of course it will also help you to do camera pose estimation, right? So there's kind of iterative joint inference, which you go through a number of iterations with the program and the camera pose estimation to help each other, to allow us to solve two things, both inferring these camera poses, the pitch and yaw, and to do the things we did before, that is searching for programs that explain the centroids of these detected repeating objects, and to try to reconstruct the image. So it turned out having this kind of a joint inference procedure allows us to do two things at the same time and do both better than previous methods. Of course, assuming, again, the constraints here is we assume we're working on images with such kind of regularity structure, which is not like all the natural images. A lot of natural images don't have this kind of structure. So for camera pose estimation, we achieve kind of a lower errors compared with earlier methods. And we can still do things like imaging painting, and which again, does better than the CLVR back then. That's 2020, I think. Yeah. So you can get the structure correct, and you try to maintain the structure, but also make the thing look realistic. Okay, so this is all about a single plane. You can see in a plane from top-down view. You can see in a plane from angle. But going back to the corridor example, then you realize there are multiple planes, right? So walking in a corridor, there's ceiling, there's floor, there are walls. So you want your method to generalize to this multiple plane situation, not only working with a single plane. So how could you do that? It turned out, with some assumptions, we can still do that. But here we have this box assumption, where what it means is you assume you're in a box, which means there are like 4 or 5 planes in front of you. So what we want to do is you have to infer the camera poses, and at the same time you want to infer the orientations or the surface normals of these multiple planes. And for every plane, you try to infer their positions and surface normals, and you can rectify it. You can do the things that we did before. You can rectify it, try to infer a program like representation to explain every plane. Okay, so here you can see in the ceilings, the lights are repeating themselves, and that happens the same, the same thing happens on the walls, because the lights or the shadows also repeat themselves as well, right? So of course, but this problem is now much harder, because now you're really more in, it's not real 3D, but you have to have more knowledge of 3D. So what we did here is we first use some kind of lower level visual cue extraction, right? So just like, okay, let me first talk about this. So here what we use is we first estimate the vanishing point, and then we estimate the wireframes. These are all using existing methods from UC Berkeley, just to estimate the vanishing point of the image and to estimate the 2D wireframes. So no, of course you can also try 3D wireframes, but turn out that's not robust enough. So we just go with 2D wireframes and vanishing point as the bottom-up visual cues. So you can actually draw an analogy here, because in some sense you always need to vectorize the image. You want to work with the lower dimensional space, and you don't want to work with raw pixels if you want to search for a program. But if you want to go back eventually for image editing and synthesis, you have to be a friend of pixels. You have to have a GAN or something, or nowadays maybe diffusion models. But for program synthesis, you have to work in this kind of higher dimensional, more abstract space. So there is always a step of trying to vectorize the image a little bit. And if you look at cases of line joins, then the vectorization assumes you know the primitives, and so you're estimating lines as primitive shapes. And for single plane images, you're like, okay, now there are no lines of shapes, or you don't want to assume that, but you use internal learning to discover the repeated objects. And for the multi-plane images, or for those kind of, I would say box images, then here we're assuming, we're working with the space of the vanishing point and 2D wireframes. And once you have the higher level, I would say these kind of extracted visual cues, then you want to run program synthesis, but still, they're not totally equivalent, because for repeated object detection or for lines or primitive shape estimation, they're almost pretty accurate. But for vanishing point and wireframes, vanishing point is probably still okay. It's now pretty robust now, especially with these kind of deep network-based methods. But for wireframes, you can see that there are a lot of noises, there are a lot of signals, but also noises, and it mostly works in 2D because the 3D methods are not good enough. So then there comes the question of, based on these 2D visual cues, including the vanishing point and the wireframes, how could we infer the correct, I would say, 3D programs, or at the first step, of the plane partitions, right? What part of the image are actually a plane? Then I should go back to earlier methods about estimating their surface normals, rectifying it, synthesize a program for it. But before that, right, we have to first even partition a plane into partition an image into multiple planes. So if you just based on the vanishing point and the wireframes, then you have a number of candidates. Right. For humans, we have strong priors. We know, what a scene look like. And so we will say, okay, of course, candidate 2 is the correct one. For models, they don't have this knowledge, especially given everything here is learned on a single image, right? So there's nothing like a training set where you can get some signals about, annotations on what a scene look like, right? So, so how could we, based on the visual cues, to infer these or partition the planes correctly? So the idea here is just like estimating camera poses and synthesizing programs should really help each other, right? So the idea of inferring or searching for the bottom-up visual cues and top-down program synthesis should not be considered independently. Instead, they should be considered jointly, because they really help each other. Finding the right camera poses will allow you to get a very succinct program to explain what is really there, right? So here is the same thing. That is, finding the right program partition will actually allow you to synthesize the program in a very succinct way, in a very compact way, that you can very easily explain what is really there in the plane, and you can explain it really well if you want to reconstruct it, right? So for example, let's say we have these 3 candidates. I don't know which one is the best option to partition the image into the planes. What I can do is I just take each of them, and then I can say I just run whatever I had before, estimating the surface normals for each plane, trying to rectify them. And after that, you get these kind of rectified images for each plane, and then you can do a program synthesis on top of that. But then you notice that only with the correct plane partition, just like only with the correct camera pose estimation, you're able to the plane, the rectified plane will look much more regular. There's kind of strong regularity prior, and the synthesized program will be able to much better and will be first much shorter, much simpler, but also much better explaining what are there in the images or in the planes, right? So if your partition or if your rectification is incorrect, then you get images that clearly doesn't look as regular. So programs will have a hard time explaining them if possible at all. So here again, the bottom-up signals, and plane partition and program synthesis should really help each other. And you can use the knowledge of, what a program look like and how well it describes the planes to help you to select the lower level things. That is, based on the vanishing points and wireframes, what is the correct plane partition? So with this kind of plane partition and surface normal estimation program synthesis, what it can do, of course, again, for all these kind of higher level structural stuff, you pair them with the lower level image generation models like again. So it allows you to do things like visual synthesis. So you have a corridor, you can go forward, and in the short term, everything looks good. But in the longer term, by having those kind of structures and tells you what should be there, you don't have that much kind of distribution drift. You can synthesize going forward, the images look pretty nicely. And you can do other things like, what if I want to look to the top left, right? So you will expect, there should be another light coming in. And, by having this kind of program like structures paired with GANs or, primitives for GANs for synthesizing the primitives or patches, which are the lights here, you're able to synthesize another light coming in. While the more general view synthesis methods don't have this kind of priors, and they cannot do it. But again, they're designed for more general scenes, right? We're designed for more specific scenes. So of course, if you train or if you run all these methods on more general scenes, then our methods wouldn't do better, right? Because we rely on the assumption that there are structures like this in the image. But when there indeed are such kind of structures, we can do much better. And you can do other things like, what if I want to walk backward? Then there again will be lights coming in, and as well as the shadows on the walls as well. And you can say, what if I want to turn around, right? And I'm only seeing the first half of the corridor, so there's no way for me to really understand, what is really in the back, and there are infinite hypotheses. But if I have to pick one, then I would say, maybe I would just pick the one that is impossible, but most plausible to me, that is there's an infinite corridor. So you can just, everything should just repeat themselves again and again, right? So this project actually originally motivated, Carl must know, MIT has this infinite corridor where there's a very long hallway that you can go across multiple buildings. So I feel like, yeah, if you're seeing the image, in a hallway from one side, you should be able to synthesize the other side. So can we generate an infinite corridor from a single image? So that's the original motivation behind this project. So you can indeed do that. There's no infinite corridor in the world, but you can synthesize something that's, hopefully makes intuitive sense. And you can do it for image extrapolation for buildings, because if you think about having walking in a corridor is you're inside a box, then seeing the building is you're seeing from the outside of the box, right? So the only difference here is now you have 2 vanishing points instead of 1. And you have the input image, and you can do things like, these are the baselines for, if you want to make it taller. Some of them, they do a reasonable job, but sometimes they don't really expect the input image that well. Or sometimes, yeah, they just don't look as realistic because they are not aware of the 3D structure. But our methods can do that. This is, what I showed at the very beginning. So this is joint work with Sharon Mao and Yikai Li for all the previous 2 or 3 papers I talked about. And Jiajun is now an MIT PhD student, and Yikai is now a Stanford PhD student. Okay, So as a quick recap, we talked about how this kind of visual program synthesis idea can be used first in very simple scenes, in 2D primitives and 3D primitives, and then maybe incorporate with single image learning or single image scene editing, and then with camera pose estimation, and then going from single plane to multiple planes. So what's next? So in some sense, we can think about it as single image learning is now we're doing everything 2D, and for camera pose estimation, it's like you have a little bit of knowledge of 3D, also maybe that's like 2.1D, and with multiple planes, it's still not fully 3D, but now at least you have the notion of managing point in multiple planes, right? So in some sense, you can think about it as you have like a surface normals or of the image. So maybe I would say that's more like 2.5D. So of course, very naturally, you want to say, okay, is that possible for us to do in 3D? Right. So especially shapes, like natural images, we have all the structures because it's humans, they build all those buildings, they constructed all the buildings, right? So for artifacts like chairs, they're all man-made. And of course they have this kind of abstract and program-like structures. Looking at this table, then clearly the top is perfectly circular, and the legs are rectangular, like they're like cuboids, but they're also identical to each other, right? So it would make a lot of sense to try to capture those kind of program structures in natural shapes. And there are a lot of work on computer graphics, for example, on using L systems to generate those kind of branching structures, using very compact program representations. You can, this is not even program representation. Using very compact grammar rules, you're able to synthesize like pretty natural hierarchical structures, branches, and using symmetries or probabilistic CFG to reconstruct a shape, especially or repair a shape from partial observations. Right. So there has been also other works, now more recently, like this is from MIT as well, from Wojciech's group, on searching for programs, given the shape, can you searching for CSG, constructive solid grammar, that explain the shapes, using these primitive operations like unions or subtractions. This one doesn't really have learning. It's just like purely based on optimization. But now later people have also built a kind of larger scale data sets, which make learning possible if you want to, like Fusion 360 galleries, where they have a lot of objects and also have the constructive steps about how these objects are really made. So I don't have time to go into detail on this work, but very quickly, the high level idea is, we try to think about, is it possible for us to deal with learning? All right, so earlier methods, they're mostly not based on learning. And so now we have, neural program synthesis methods, and can we do that with learning, which then you will be able to leverage the power of data and also enables the possibility of eventually learning it from 2D images, although we didn't do it in this work. So this is mostly still learning just purely from a collection of 3D shapes. That is, we have the idea of, we have a neural network program generator that synthesizes a program from the input shape. And then, you want to close the loop. So you have this kind of program executor, but you want to make the program executor differential as well, so that you can do more like self-supervised learning, right? You can, train in for the program, but you can execute it to reconstruct a shape. Then you don't really require supervisions anymore. Otherwise, you have to rely on supervised annotations of the program for shapes, which are incredibly hard to obtain. But to make it differentiable, there are some recent work actually pretty interesting on making these kind of program execution steps differentiable. But another way of making differentiable is to, again, approximate it with a neural network, right? So we can also pair a neural program generator with a neural program executor that execute the program and synthesize the shapes. Then we assume the shapes are all organized based on specific domain-specific language. So it's like, in some sense, our idea of what these these furniture should look like. So the benefit of having this kind of program-like representation is, let's say if you have a single image reconstruction, shape reconstruction method, you take an image of the table, you can reconstruct the table, they look kind of pretty good, especially if you look at it from the input view, then they look almost identical. But if you look at it from a different view, then you realize, okay, although it looks the same with the input image, it doesn't look as natural to me, just because I have this kind of strong inductive bias prior that the table is man-made and the top of the table should be round, right? But if you represent objects instead of using these kind of voxels or meshes, but representing it with a program-like representation, then you capture the structures, and at the same time you also maintain the faithfulness. So it still looks pretty close to the original input image, but the structure looks just more natural. There has been some follow-up work to this as well, and especially Daniel Ricci has been working a lot on this direction from Brown. We have some work as well, but it's still ongoing. So hopefully next time I can talk about this in more detail. But welcome to I'm happy to chat offline as well, and also in some of the one-on-ones afterwards. Okay, so finally, I want to talk about something that I think I'm more excited about. That is, so there's a question about, we talk a lot about how we can synthesize these visual programs, right? Synthesizing it for a single image, and then, going from 2.1D to 2.5D, and even for its 3D. But the question, there's a more important fundamental question, that is, why are the programs there, right? So I think I've suggested a few times throughout the talk that, there are actually no perfect program structures in the natural world. There are rarely any perfect spheres or circles in the natural world. Maybe one exception is the moon, but otherwise you just cannot see that many circular stuff. But somehow there are a lot of them in our daily life just because we fabricated them ourselves, right? Because humans have these preferences in the fabrication process for some reason, that we want things that are regular, maybe for aesthetic reason or for practical reasons. So what are really program-like, or what are really structured? And if we look at an example of this image of a vase, and then you're like, in computer vision, we care about this problem of intrinsic image decomposition, right? So you have an image, we know there are a lot of intrinsic images like surface normals, albedos, materials, diffuses, specular maps, and environment maps, right? So, if you can really get all these structures right, then you will be able to do a lot of other things like image relighting and null synthesis and stuff like that, or shape editing. But what part of these intrinsic images are really, I would say, program-like or structured? I think that has a lot of connection with the human fabrication process, because if you look at surface normals or the shapes, right, it is kind of perfectly rotationally symmetric, just because when humans build it, they have this, they want it to be, they made it rotationally symmetric, or they have their specific tools to make it rotationally symmetric, right? So we have this kind of very strong prior that is, okay, it's explicitly, this thing should be regular. And the same as material, because, although this thing looks, textures are kind of pretty different everywhere, but we know it's made of the same material, which is probably like porcelain or something, right? So by material, that means it also have the same reflectance functions everywhere, right? So although, some part are much brighter, has specular, but we know that they all have, every point on the surface has the same reflectance functions, right? So you have this kind of strong priors, I would say explicit priors on the regularities on surface normal, shape, and material. So what about albedo, right? So this vase looks to me like, yeah, it sort of have, very similar textures, right? The textures are regular in the sense that, yeah, I would say it is the same texture everywhere, but it is not like a same in the sense that it's pure color, right? It's not like every pixel on the original image or even on the albedo map are identical. They're actually pretty different, right? But they have this kind of perceptual similarity in the sense that when we build it, we want it to look nice, not nice in the sense that it's pure color, but nice in the sense that it's, uniform texture, uniform in a way that is perceptually similar, right? So I would say there's kind of a little bit of implicit regularities in albedos or in the colors of the objects. And, of course, there are other things like lighting, especially if you capture in a kind of very constrained environment, there are irregularities on lighting as well. But in general, especially indoor, we'll assume that the lighting are just much more complex, and there are a lot of reflections going on. So we'll just assume the lightings or environment maps are not regular. Okay, so you can see that there's actually a little bit of slight asymmetry here, right, on the regularities introduced by humans in these different parts of intrinsic images. And now the question is, is it possible for us to leverage this kind of very slight and subtle asymmetry to do something that we cannot think about before? That is, do very strong and, I would say, to just solve the problem of intrinsic image decomposition with strong performance, right? The problem of intrinsic image decomposition is really hard and highly ambiguous, right? Because you're trying to get multiple images from one, and there are infinite number of explanations from a single image, right? What is albedo? Is it flat, or is it circular, stuff like that? Oh, sorry, surface normals. Is it flat? Is it circular? Or so there are infinite number of solutions, explanations. That's why this ambiguous problem is really hard. But now we have some signals, right? The signals come from the asymmetries that humans introduce in the fabrication process. So it's possible for us to leverage this kind of biases for image staining and decomposition. So we're inspired by this earlier work, the CVPR 2020 best paper from VGG, and the first author is Shangzhe Wu. So what they did is they have this kind of single image and of the face, and they want to sort of try to infer the 3D shape of the face, but they want to do it without supervision. So what they did is, they can decompose the image into these confidence maps, but more importantly, there's viewpoints, depth, and lighting, and albedo. Okay. Then they notice this kind of important signal that is human faces are symmetric, reflectional symmetric. So if it's reflectional symmetric, what does it mean? It means if I flip the face, but what you're really flipping is you're flipping the depth and you're flipping the albedo, right? So you're flipping the depth and albedo and of course the confidence map, but you're not changing the camera viewpoint and you're not changing lighting conditions, right? So, but only by changing a subset of these things, the whole image should look the same, right? Because with the same lighting, but you only flip the albedo and depth, then you should get the same image, right? So then, so this kind of constraints allows them to actually train a model that learns to decompose the image into depths, and because now it's no longer that ambiguous, right? You now have additional constraints what the depth of albedo should look like, because when paired them with lighting and camera parameters, it should look like the original image. Okay, so what they can do with this kind of smart design is you're able to going from single image to infer the surface normals and albedos, so you can do novel synthesis and 3D reconstruction, right? This is with Ilya Wu, who was student at VGG. So then we thought that's in 2020 where I was at Google, and then Ilya coming and did an internship with us. So we thought, is that possible for us to going beyond from using symmetry for shape recovery to using structure for image de-rendering, right? So is it possible for us to leverage this kind of asymmetries in the design of the surface normals and materials and albedos, right? Some are explicit, some are implicit, to also to decompose the image, to do intrinsic image decomposition, and allows you to once you can do that, you will be able to synthesize the novel view of the base from just a single image. And if you can do material and diffuse and spectral model estimation, you can also do relighting. I think there is a little bit of okay, you can probably still see it. Okay. So what we did is, we really try to leverage, at least this is my version of it. People present it differently, but when I present this work, I present it from this angle. That is, I think we really leveraged the idea of, there's kind of structure, explicit and implicit regularities. For example, for shapes, right? Because human made it to be rotational symmetric, so you can actually parameterize it with a solid revolution representation. So you have SOR representation. You can parameterize the shape using just like 1D vector, which is the radius of the radius of the objects along this axis, and with camera pulse estimation. And once you have the shape, you can unwrap it, so you can get a surface normal image, you can get a texture image, and then you can do relatively standard lighting, material estimation, albedo estimation, just like every other work in intrinsic image decomposition. But the idea that is the objects is fabricated, it must have the same material everywhere, so you can parameterize the materials using just like very low dimensional representation like alpha and rho, which is for the reflectance function. And you have, lighting, material, and albedo. And, you can put them back, you can re-render, put in the shape and the lighting and material, you can re-render and get the diffuse and specular components, and you can eventually put it back with albedo to reconstruct the textures. Okay, so then you have this kind of reconstruction loss. So whether the decomposed image are really decomposed intrinsic images are really explaining the original input image, right? So these are the second part is kind of pretty standard to, I would say, existing intrinsic image decomposition methods. But one thing that we haven't used is we have talked about, right? There's explicit regularities on the shape and on the surface and on materials. So we have already been using these kind of signals in the parameterizations of the shape and in the parameterizations of the materials. One thing we haven't used is albedos, right? It's also something textures. It's also something that human made it to make it look kind of uniform, although they're not pixel level similar. So you cannot really assume that every pixel has the same albedo. But what you can do is, because it is sort of like implicitly regular, so we actually added two additional, I would say, constraints or loss functions. The first is, it's not like every pixel is the same, but they look roughly the same. So what if I just compute a mean albedo, and then we reconstruct the original image with the mean albedo, also put it back with lighting and materials. And now the mean image, although not identical to the input image, they should look reasonably similar, right? So you can still compute this kind of L2 distance between the mean albedo reconstructed images and the input image. Okay, but what is more important is the final loss. That is, what it means by albedo to be, I would say, to be regular, right? In a sense, it's not like every pixel is the same color. It's like more like perceptually. If I look at it, then I can now tell, I feel like every patches, they all look kind of similar, right? So especially, if I take the albedo, and then no matter whether the patch of albedo comes from a region that is highly specular, or it comes from a region that is not specular at all, then the albedo shouldn't be impacted by that. The patch of albedo map that comes from highly specular regions and low specular regions, they should look kind of pretty similar to me, or at least to anyone in a perceptual sense. And when you translate it into a neural network, that is, now you have a discriminator, right? You have a perceptual loss, you have a discriminator that is self-supervised. And so how it's implemented is like you have these predicted albedo images, you have the predicted specular images. And you can sample a number of patches on the albedo images based on the predicted specular images, right? So there are regions that are highly specular, there are regions that are not as specular. And you can you can have all these random patches sorted by the variance of their specularities. And then the question is, if I have patches from least specular regions, patches from highly specular regions, the discriminator should not be able to tell if the patches are from a least specular region or from a highly specular region, right? So no matter whether, I think this is actually really addresses the big problem in intrinsic image decomposition, because once you have when the specular is really high, then often the image is really overexposed. And if you look at RGB values, it's like 255 or something. It's pure white, right? So how can you go from pure white pixel to actually get the underlying albedo pixel, right? So albedo values, which is really hard. But by having this additional constraint, that is, no matter whether the patch is from a highly specular region or from not specular region, the albedo image should look identical. You sort of, the discriminator should not be able to tell. You actually sort of constrain the albedo to really look, perceptually similar. In some sense, I would say implicitly regular, in a sense that is, that really helps us to break, I would say, the ambiguities in this problem. Okay. So you can put this additional loss, on top of the mean reconstruction loss, the reconstruction loss, and the silhouette loss. So I would say, again, the surface, the shape, and the surface normals and the materials, we're using this assumption that is, the code or the structures of the objects in the fabrication process are explicitly introduced. And for albedos, we're using the knowledge that is the code or the structures of the objects are implicitly introduced. So here again, everyone wanted to talk about symbolic stuff. They're like, this is really hard to optimize, this doesn't really generalize. But I think it's, in many cases, people interpret symbol or code in a very narrow way. So here, when I say code or symbols, it can be interpreted very broadly, in a sense that we have some structures or ideas about how these albedos can be constrained. It can be purely in some sense, right, constrained by a neural network, but that's also based on the observation that it is made in the sense that albedos are made to be implicitly regular. Okay, so you put all these things together, you can do, going from an input image, you can do intrinsic image decomposition. You get surface novels, albedos, diffuse maps, specular maps, materials estimations, and environment maps. And with all these decomposed images, you can, going from a single image, in some sense, you can say like we can virtualize it, right? Going from this image, you can virtualize it. You can see it from different views. And you can rely them. So here are some harder examples where the images are out of distribution, never see them from different data sets. And some of them are painting, some of them with some text on it, right? So we're not dealing with these texts very well because again, we have a solid resolution, yes, that's right. Solid resolution assumption. So we can still do interesting image decomposition. We can virtualize the image. You can see some of them are paintings, and so you can virtualize them. You can see it from a different view. So again, the tags are not really tackled that well, but in general, it looks pretty realistic to me, at least. And you can relight the scenes. Okay. Yeah, so in terms of 3D, right? So we can model the 3D structures of objects by using programs. But also, if we're thinking about why the programs are there in the first place, then we have a more broader interpretation of what programs or codes are, and allows us to do other things like even lower level image processing problems like novel view synthesis and relighting. And something I don't have time to talk about, I'm not going to talk about it, but I think it's also interesting, is we also try to capture the structure of program structures in temporal domain, like human doing exercises and motions. There are a lot of kind of structures there as well. Okay, so to summarize, right? So I think our key innovations here is we pair neural networks, which are very great for recognition. Recognition can be reconstruction, can also be discrimination, right? But with some kind of program representations for generalization, right? A program can be interpreted or realized in very different ways. It can be explicit programs, it can be for loops, or it can be sort of I would say more implicit, like the structures that we have about about the natural world, about the artifacts that we made. So what is next? Everything here is still kind of more or less constrained, right? They're constrained different ways. The buildings, you have to assume there's a building, you have to assume there's a base. It's like the rotationally symmetric. So is that possible for us to go beyond to deal with more general scenes? Like this is a screenshot from movie Inception, where you see all the columns, they're clearly rectangular, so clearly repetitive, but there are also other things that are not as structured, like the skies and the trees and the background and stuff, right? So how to put them together with more general, I would say maybe more neural methods. And the methodological level, what is the real role of symbols and programs? How they can be implemented or realized? Do we really need them? To what extent? And whenever you want something that's more structured or symbolic, you always come with the problem of optimization, because that makes the optimization landscape much more non-convex. And it's just really hard for things to especially even neural networks to get to the right position. Or you rely on search algorithms, but they're just really slow. So can we come up with more smart and efficient inference algorithms? And all these are based on perception. So can we go beyond perception to action or interaction with the scenes? The notion of symbols, they have clear connections to humans use them to reason, and they're grounded in language, right? So is it possible for us to establish those connections as well? Yeah, that's it. Thank you, everyone. Thank you. So any questions?
Great talk, Jiajun. We'll open it up for questions. I can start with the first question, actually. So related to one of the previous projects, the ones with the plane that you talked about, it seems like an assumption is that each of the individual surfaces are very regular. Like you mentioned, like here with the trees, for example, it wouldn't be. But we don't even have to go as far as trees. Even there could be like walls which have irregularities in them, or like maybe cloth surfaces, I don't know. So, but they would still have the vanishing point if they're aligned along the line, I guess. But the surfaces may be irregular. So do you see your method still working for?
Yeah, I think of course, yeah, that's a very good point, right? So, and clearly directly applying our methods will not work. So in some sense, what you're saying is very similar to this picture, right? So here, there's something that's you can see the columns. In some sense, there is a plane here, but between the columns, right, between things that are repeating themselves, there are trees and stuff, and they all look kind of different. And so here there's no solid wall, right? So there's actually even more, and even within the the columns, we know they're the same thing, but some are under shadow, some are fully lit up, so they also look different, right? So clearly directly applying our methods will not work, but hopefully we will have some smart ways of connecting them with more general methods. One idea is if you look at this IDEA paper 2020, right, they have this confidence map, right? So we're like, which part of it should be taken care of by structures, which part of it should be taken care of by just like purely neural network methods or stuff.
Yeah, very interesting. Yeah, it could be a nice combination of structures versus priors that you've learned from a lot of data, and I guess how to control that. Yeah. Looks like Shudong has a question. Go ahead.
Yeah, thanks a lot for the great talk. I guess I have more conceptual level question. So I'm also working on something related to like representing videos or video frames with a sequence of text tokens. And every time I do this kind of symbolic or structured representation, I will have questions from the reviewers, like if this kind of representation will inject some bias from the human side to the model, right? So I guess there might be similar problems for the programs as well, right? So, I mean, although the structures like the normal albedo, they are definitely physics-based, but I just wonder if you see any possible limitation if we just design these kind of structures by ourselves, although this might be motivated or supported by some physics. Yeah, but I just wonder if you see any possible limitation or bias could be injected through this kind of structured design.
I think it's clear that at this moment, even Josh Sullivan would say most of the things should be learned. So it's clear that you don't really need that much structure. But sometimes you may still need a little bit of structure, right? There are a lot of things I can say about here. So one is, yes, as you pointed out, right? A lot of things are grounded to physics. A nice thing about grounding them to physics is that means they're universal, which means that any image you take, if you take a picture of whatever scenes you have, right, there must be some surface normals there, right? So it is kind of a universal representation. So at least it applies everywhere, right? It is not like defining an object category, which then there's a new object I've never seen before. I just didn't generalize, right? So that's one benefit of that. And the second is, maybe one argument could be, I'm not saying this is what we should do for neural networks, but I think that could be a valid argument. That is, eventually there's this kind of through millions of years of evolution, right? There is something that is going from being learned to become innate, just because that's more efficient or stuff like that. And people may argue the notion these are very minimal stuff, but people may argue these things include the notion of objects and the notion that there's depth and the notion there's surface. So maybe these I think it's always very hard to test if anything is innate or not, but it's relatively easy to test if something people already know it in a very I would say first few months of their life. So if people at least know them in the first few months of their life, then that means they're either innate, which means if you want to really rely on human knowledge you want to be human inspired in building AI systems, then maybe they should also be innate in your network architecture or the system in general, or they should be introduced with some correct inductive biases so that they can be picked up very quickly. Yeah, I think these are I don't know. Yeah, I think there's one more thing I wanted to say, but I forgot. So maybe that's it. Yeah, that's okay. Yeah.
Go ahead, Mia.
People in the chat, because
So there's one thing. There's just Samir who raised his hand. All right, Samir, go ahead.
Yeah. So it seems like, in like a lot of this line of work, it's trying to pick up structure from like the regularity in images. And I'm wondering if you've thought about like using language. So language is perhaps another way that you could provide the structure of an image, and sort of like, do you see extensions of this line of work incorporating like sort of language modality as well?
Well, yeah, just like pointed out here, so language itself, it clearly has some symbolic structure, but I think it's not. There is a little bit of discrepancy here, so which makes me feel like the extension or connection is not very straightforward. in some sense, it's also, you know, sort of, you know, if you look at it, I think there is also a reason that why all these neural network methods or embedding based methods are very powerful, especially in natural language as well. Because you know, I think you come up with a word for you come up with a word, yes, word, for the need of communicating with each other. So you want to refer to something, and something can be, you know, in a lot of cases can be based on semantics. And everything we talk about here, maybe as in my response to, I would say, Xudong, is I would say more grounded on physics. And humans' understanding of physics is kind of smart in one way, but also limited in many other ways. And we don't really talk about it as much. So when we talk about it, I know it's mostly about object semantics and stuff. And what is a chair, or what is you know, yeah, so these are really hard to define. So I don't see they directly connected to, you know, anything I talk about here, because this is more about the geometric and physical structure. I think the notion of symbols that try to connect language and vision could be interesting in other ways, but that may be a totally different talk.
Cool, thank you.
All right, thank you, Jiajun. We'll move to the one-on-ones.
Okay,
Yeah, so
great, thank you.
one-on-ones, but yeah. All right, thank you so much for the talk again. So.
Thank you. Yeah, thank you, Carl. Thank you, Perry. Thank you, everyone. I'll